Okay, hi everyone. We are starting week 5. And this week we are going to continue looking at convolutional neural networks, and then we will start with recurrent neural networks. We will actually complete recurrent neural networks this week, and we will have completed the fundamentals in 5 weeks. In the syllabus, I planned it for 4 weeks, but it took 1 extra week. But it doesn't matter. Starting from next week, we will start with self-attention and transformers and other advanced topics. Last week, we looked at convolutional neural networks. We looked at padding, max pooling, AlexNet, convolution, how to implement backpropagation in a modular manner, and dropout, rate augmentation, etc. This week, today, we have some CNN topics again. We will talk about how to implement a convolutional layer efficiently. We will look at important CNN architectures, for example, ResNets. And then we will look at types of convolution. There are different types of convolution operations. We will also look at normalization layers, such as batch normalization, group normalization, instance normalization, and so on. And then most of the time today will be devoted to recurrent neural networks. We will look at basic RNNs, backpropagation through time, and the challenge of long-term dependencies, and gated RNNs, such as LSTM and GRU. Recommended reading for this week is the ResNet paper, Deep Residual Learning for Image Recognition. This is a highly influential paper with hundreds of thousands of citations. I think each one of you should read this paper. It's a very important, historically important, and still very relevant today. We are using ResNets all the time. So, and it's a very good paper, very good read. Highly recommended if you did not read it already. Okay, let's talk about how you can implement a convolutional layer efficiently. If you don't care about efficiency, you can do a naive implementation such as this. There are four loops nested in each other, and it's a very straightforward implementation. The outer loop goes through the rows, this one goes through the columns, and then this one goes through the rows of the filter and rows of the columns of the filter, and then you just take a multiplication and record it at output row column. Now think about how much time and memory would this implementation consume. The time complexity is very high because there are four loops, and it depends on the image size and the filter size, right? But there's some power of 4. So it's very inefficient. But what about in terms of memory? You have to only, it is efficient in terms of memory because you have to only keep this output matrix in memory, and that's it. It's actually very efficient in terms of that. But when you compare this, the time, execution time that it takes for this naive implementation that I showed you. So the red plot is the implementation that I showed you in the previous slide, and the blue plot is the PyTorch Com2D's time complexity. And x-axis is the size of the input, n by n, size of the input image, let's say. And as you can see, this is the log scale in terms of time. The naive approach does not scale well, as you can see, but the PyTorch implementation scales well. And now we are going to talk about how you can get this blue curve. Does anybody know how? How you can make it efficient? Vectorization and matrix multiplication, right? Exactly. So it can be implemented using matrix multiplication instead of implementing convolution using for loops. Advantages are we can make use of the highly efficient linear algebra packages because these packages have highly efficient matrix multiplication routines that we can use. Disadvantage is we will require more memory. And let's look at an example. Let's say our input is 200 by 200 by 3 image, and we are convolving this with a 10 by 10 by 3 kernel. Okay, so this is our kernel, 10 by 10 by 3, and we are going to use 75 of them with a stride of 2. Okay, now what would be the output dimensions if I do this convolution? Hmm? Yes, it's around 200 divided by 2 because of stride 2, but let's be exact. So I don't want to memorize formulas, but this is 200 and my kernel is 10, right? And at each step, I move it by 2 locations. So this is n is equal to 1, let's say n is equal to 2, n is equal to 3. It will be here. So when n is equal to 3, there will be 4 locations here, and this is still 10. So it looks like, so n minus 1 times 2, which is the stride, plus 10, accounting for this 10. We will do this for up to 200. And then from here, we get 96. So this is 96. This is 96. And who can tell me what this dimension is? Okay, any other answers? 75, yes, because we are using 75 kernels 10 by 10 by 3, and that output channel dimension is determined by the number of filters that we use. Okay, so this is the standard convolution. Question? Yes. Yes, one filter will give you just one output, and 75 of them will be 75 outputs stacked in these channels. Okay. And okay, so this is the naive, plain convolution. So we just computed the dimensions of this, but how can you implement this using matrix multiplication? So what we will do is take this multi-dimensional array here, 10 by 10 by 3, and this will make a 300 by 3 vector, right? So we vectorize that part of the input image, and we stack this into a matrix as a row vector. So this first one is the first location vectorized. The second one is the second location vectorized with a stride of 2, and so on. So this will be the dimensions will be here. It's 300 And here it's what's the dimension there? So this last one is actually vectorized and put into here. Okay. Yes, 96 by 96, and it's I think it was something like 9,126. Because that's the number of all locations in the applicable chip. Now we are going to multiply this with the vectorized form of the filter. So we will vectorize the filter into a this will be now this will be a 300 by 1 vector, and then I will repeat no, there are 75 of them, right? There are 75 filters, so the number of columns is 75, the number of rows is 300, and at the end, I will get a matrix that has dimensions to 9,126 by 75. And then I will reshape this to 96 times 96 times 75, and we are done. And by doing that, yes, you are consuming more memory, but this is, in terms of time complexity, much better. It scales very well with the size of the input image, as you see here. Okay, so this is actually how the convolution is implemented in major deep learning libraries. Yes. Yes, if the stride is smaller than the dimensions of the filter, then the filters will overlap, right? I think, yes, it has a benefit. It covers the input densely. So if you make a stride 10 here, then you might be missing important information in between the filters. Yes, this is usually, the stride is usually less than the filter size. Okay. So this is how convolution is implemented in any serious implementation. Now let's look at some types of normalization layers, and the most famous of them is batch normalization. Introduced in 2015. Again, this is a very highly influential paper. It has more than 63,000 citations as of today. And here is what it does. As input, you take a example, mini batch of examples. There are M of them. And what batch normalization does is takes the mean first here, taking the mean, calculating the variance, and then transforming all the examples based on mean and variance. And when you do this operation, your batch becomes zero mean unit variance. You see that, right? When you take the mean of your batch, it will be zero mean, and the variance will be 1 unit variance. After that, it applies a scale and shift parameterized with gamma and beta, and these are learned. So it applies a learnable scale and shift on top of zero mean unit variance batch. So same thing, normalizes the input at each batch, makes them zero mean unit variance, and then applies a learnable scale and shift transformation, and these are the learnable parameters of batch normalization. Why do we do this? First of all, applying this technique is usually done by inserting the batch norm layer immediately after the fully connected or convolutional layers before nonlinearities. This is the usual practice. And it has become a very common practice to use batch norm in many high-performing networks. You could see batch norm layers. Networks that use batch norm are observed to be more robust to bad initialization. So it also covers some other problems. Also, it seems to regularize the model. In this 2015 paper, they discovered that batch normalized network, in a batch normalized network, we found that dropout can be either removed or reduced in strength. So if you have batch normalization, the effect of dropout, which is a regularization method, is reduced. Here's a question for you. What happens as M gets smaller? M is the batch size here. Think about it. If you have a smaller and smaller batch, what will happen? Yes. As you go to smaller batch sizes, the variance here will be high, right? And the batches that you get will be less and less representative of your data set. They are already not very representative, but as you make them smaller and smaller, you will get less and less representative batches. And here is what happens. Y-axis is the error on some supervised image classification data set. This is ImageNet classification. And the x-axis is the batch size. And towards right, it decreases. So it's a kind of a weird plot, but as you decrease the batch size, if you look at the blue curve, which represents batch norm, the error goes up. Okay, and because of that problem, the variance is high and it becomes less representative. But with something called group normalization, which we will see, it is stable. So obviously, batch norm depends on the batch size. Okay, that's the, yeah. What are they for? So the question is, what are the learnable parameters here are for? It learns the optimal scale and shift for the next layer. That's all I can say. Depends on the task, problem, and the network. It finds some optimal values. But relating to that parameters, I have another question. What do you do at test time? But
what if you have a batch size of 1? I mean, when you apply batch
it won't work. Batch size 1, of course you can do it, but then you will get a very bad performance as shown here. With batch size 2.
But I'm asking about generally, like the batch normalization is already implemented in the network. But if you select the batch size of 1 records,
what do you mean it's already implemented in the network?
Generally, when you implemented network, there is general batch normalization implemented.
Okay. So yes, you are. I think you are asking this question. We have a network that is trained with batch normalization.
It's already implemented with batch normalization before.
Okay.
So and when you train by utilizing any function in way, the thing I'm asking what happens if you select the batch size of 1.
I would say with a batch size of 1, you would get very bad performance.
Normalization becomes 0 over 0. So it depends on the error value, I think. So it becomes very shading, normalizing only one value. mean is the
That's right.
baseline.
The variance will be 0, right, with one example. So you will get 0 in the denominator because of this epsilon, which is added to prevent division by 0. You won't get an error, but your values will be very high and yeah, it won't be stable. But related to your question, what do you do at test time? So we have these learnable parameters. They are fixed, right? They are fixed. Because during training, your network estimates these alpha, gamma, and beta parameters, their optimal values. And then once you go to inference test time, you have to fix them. You don't want to learn them again. And also, oh yes, okay. And to do that, in PyTorch, you have to say to the network that you are now in the train mode or you are now in the evaluation mode. If you forget to call this eval function, then it will keep learning gamma and beta during test time. And this is a very common mistake that students make or researchers. Since it continues to train during test time, you get better accuracies because it tries to overfit to the test data set. Still, you have to make this eval. So after training, during training, you should call this. After training, you should call this. So yes, be careful. Also, this applies to dropout because during training, you have to randomly kill neurons in the train mode, but during evaluation mode, that should not happen. Okay, so if you forget to call this, then weird things happen. Yes, very good question. Your friend is asking, during evaluation, what happens to these mu and sigma? What do you think? Yeah. Yes, they are pre-computed from the training set and they are stored. Yes, because during inference, you may think that these are computed for the test batch, but during test, you can just change the batch size. You can make it 1 or higher. So the answer is yes. These things are computed. These are statistics of the training set, and they should be computed and stored. And in the evaluation, these are used. Okay, but batch norm, very useful when you have large batch size, but if you have to use small batch size, then there are other normalization methods which are better. If you think of your mini batch as a multidimensional array, let's say this dimension is the height and width of your input, and this is the number of channels, and this is the number of examples. Batch norm is doing a normalization in the n dimension. It takes a mean over your examples. Okay. Layer norm, on the other hand, takes a normalization in the channel dimension, not the example dimension. Instance norm takes the average of each example, and group norm does something in between. It's very flexible. You can, so it's never in the data dimension. So you abandon that. You don't normalize with respect to your batch size because of these obvious problems. But you can normalize with respect to the channel dimensions and the examples within themselves. And this is called group normalization. It is also a highly influential paper. It's being used in many networks today. Implementation is very straightforward. I won't go over it, but it's straightforward implementation. Again, you have the gamma and beta parameters, learnable. So those are the same as batch normalization, but the normalization is done on the channels and the examples. I believe this is the examples, not through the batch dimension. How does normalization solve?
Normalization is better.
Uh-huh.
Batch size.
Yes.
This is the normalization about RNNs.
You are talking about the variance of what?
Batch.
Batch. No, there is still a mini batch, but the normalization is done over individual examples and their channels, not through the batch, not over the examples. So its statistics is not calculated over the examples, but within examples. Yeah. Okay. If no questions, let's continue. And this is a plot from the group normalization paper. On the left, you see the batch normalization through epochs. And different curves, different colored curves show different batch sizes here. And as you can see, the largest error is with this batch size of 2. And the lowest error is with the batch size of 32. But with group normalization, your errors are similar, independent of the batch size you use. So that's a nice property. Because for some problems, your GPU memory might be small, or your network might be too big, then you have to use small batch sizes. In that case, you should go for group norm, not batch norm. Yes. What is the advantage of batch norm over group norm? Group norm is better, yes. And group norm is newer. It's 2018, batch norm is 2015. I wouldn't use batch norm if I were to create a new neural network, because group norm is shown to be better. But if you have very large batch size, then it won't hurt to use batch norm. It's not a problem. Okay, now let's look at some important CNN architectures. And we will do that through the image classification ImageNet benchmark, which is called this ILS-VRC, ImageNet Large Scale Visual Recognition Challenge benchmark. It had 1.2 million images consisting of 10,000 categories. The competition was held between 2010 and 17, so it's no longer being done because at this point, 2017, researchers thought that this is solved because the neural network outperformed human performance. The task is you are given an image and your model should make 5 predictions for the dominant object in the image. If one of them is correct, then this is counted as a success. As I said, this competition is not being done, but this data set is still being used today for research purposes. But Since then, we have better and more large-scale data sets, such as this one, 9 million images in 6,000 categories, annotated at several different levels. But ImageNet still being used actively in research. So this is the winners of this competition from 2012 to 2016. As we talked yesterday, this one is the AlexNet paper, which started the deep learning revolution, because previous to that, it was around 26%. With all the combination of all the best handcrafted computer vision models, you get 26, and now suddenly you get 10% decrease. Next year, in 2013, Zeiler and Fergus actually optimized the hyperparameter of AlexNet. So this is a, let's say, highly tuned AlexNet. So there is not really a huge novelty here. It's better optimized, and you get 5% less error. But here, VGG, GoogleNet, and ResNet, they do something very novel. They do different things, and let's look at these three networks now. We'll start with VGG in 2014. And the novelty that VGG brought was, they said, let's not use filters of different sizes. So AlexNet used 11 by 11 filters at the beginning, and then later 7 by 7, and then 5 by 5, and so on. So who says that these numbers are optimal? Nobody says that. And it's very difficult to search for the optimal size. So they said, let's only use 3 by 3 convolutions and go for the depth. And during that time, it was a very good idea. So all these convolutional layers use 3 by 3 filters and nothing else. They are not larger. And by doing so, they increase the depth to, there are different versions, of course, 16 and 19. And as shown here, they get another 4% reduction by just doing that. So trying to increase the depth was a huge trend during that time, 2014-15. And that problem was actually solved by ResNets. That's the true, that's the method that worked to make neural networks really deep. We are still talking about 16, 19 years, not too deep. The other one, 2015, which is GoogleNet here, 2014 and 16, there's a V4, so it won the competition twice with another version here, but the ideas are very similar. Now let's look at what was the idea that they brought. Their idea was multi-scale processing and wider network instead of making it deeper. So the same input is processed by a 1 by 1 convolution layer, a convolution layer that has 3 by 3 filters, 5 by 5 filters, and another one that has 3 by 3 max pooling. So the same layer is processed by filters of different sizes. That's the idea that they brought, and this is called multi-scale processing. It was very costly, and to reduce cost, they use these 1 by 1 convolutions, which are also called point-wise convolutions. They basically, for example, if you had a huge number of channels here, using 1 by 1 convolutions, you reduce that C into a manageable size and then do the multi-scale processing. We will look at 1 by 1 convolutions in a few minutes. Question? Okay. So and this is called the Inception module. Inception is after this paper, it became a general idea, and it has been used in other, for example, ResNext also uses this idea. So yes, the idea was multi-scale processing. Now let's look at residual networks. I think this deserves its own lecture even because it's so influential, it's so beautiful. It's still being used today. It affected us hugely. So the question that these researchers asked was, is learning better networks as simple as stacking more layers? So we know that as we increase the depth of our network, that increases the capacity of the network because there will be more learnable parameters. But then they found that simply stacking more and more layers, for example, from 20 to 56 layer, the error went up. Why do you think this is? So you are increasing the capacity of the model. All the theories tells you that with a large number of parameters, you should get zero training error, and even and also a good test generalization. But it doesn't happen. It did not happen. Vanishing gradients, yeah, maybe could be the problem. So the answer is actually simply stacking layers. If you are not careful about how to initialize them, then you won't get a lower error rate. That was the problem. So it's as simple as that. You need to initialize these things very carefully. Otherwise, simply stacking more layers will give you a higher error, and we will see why. Okay, so this was the observation. And what they wanted to do, let's say they wanted to start with a shallow model which has 18 layers, and they wanted to insert extra layers in between. And this deeper model, which has 34 layers with these extra layers in between, they say that this should not have a higher training error because it has more parameters. To ensure that, they offer a solution by construction. So original layers, which means original layers means these, they are copied here exactly. And then the new extra layers, these guys, are initialized with the identity transform. What does identity transform mean? If you input X to the identity layer, it will output X. It won't change its input. Okay, that's called identity transform. So if you initialize, so for example, in a fully connected layer, if I implement its matrix as an identity matrix, right, it doesn't change its input. So X will come in, X will go out. This is called identity transformation. You can achieve similar things with convolution as well. So if you set this with identity, then what will happen is you should get the same training error with the shallow counterpart. Are you with me here? Because the 18 layer, this network has a certain error. This network should have the same error because the extra layers are identity. Okay, so this is good. Now, when you do this and start training, then you should, with gradient descent, with small enough step size, you should do better than this error rate. So that error rate should start to decrease. Right? But if you initialize these things other than identity, yes, at t is equal to 0, you will get a higher training error. Even you have more capacity. Okay, this is what they said. So let's put in identity layers, and then they tried to do this, but they were faced with optimization difficulties. So solvers cannot find solution when going deeper. So even if you initialize these with identity and start training from this point, they faced optimization difficulties. So they needed another solution. which achieves the same effect. And that solution is the residual networks, the residual connections. I will try to illustrate it on this toy example. So suppose that we have a neural network like this. It has 3 computation blocks, but there are maybe other computation blocks here and also in the continuation. So what I want to do is, I want to insert some layers in between this block and that block. And I wanted to implement an identity transform. Okay, because when I want to train the new network, it should start with the error of the previous one. But also, it shouldn't have this optimization difficulty. So let me show the solution. If I break this connection and take this, connect the output of this block to here, and then take this output and connect to here. Okay? So it's like surgery. Now, what will happen? Let's look at the network here. It goes through a neural network layer parameterized with W1, and then a ReLU, and then another neural network layer with W2. And then there's a plus here, which takes this input as it is and adds to the output of the small network here. And at the end, we call this HX, which computes X plus, this X plus, ReLU W2 times ReLU W1X, considering that these are fully connected layers for ease of explanation. Okay, now, just a second. Now, if you look at this formulation, when you initialize W2 with zeros or very small numbers close to zeros, very small random numbers close to zeros, then you implement the identity transform. HX equals X. Okay, so this formulation is equivalent in theory to the formulation where you set the diagonal to 1 and zeros here. But this, in practice, causes optimization difficulties. But this one does not, because this starts with zeros, W2. That's it, actually. And this is called the residual connections. This is called skip connection or residual connection.
To do that, you need to be very careful about dimensions, right?
Of course. You need to be careful about the dimensions because the dimension of X, if this is X here, should match the output or the input of the next layer. Yes. You can think of it as a constraint of residual networks.
This part.
This part?
Yeah.
Yeah, this is the idea of residual connections. I hope it's clear. It's very important. And I have a question here. Why do we need this one? And why does no? The question is why 2 weight layers and the ReLU in between? Why not just 1 layer? So why not just X something like this, right? The question is that. Mm-hmm.
Again, it's a problem.
Mm-hmm. So the answer is that there are some parts to the answer. So first of all, we need a ReLU. If you don't use a ReLU, let's say this is a fully connected layer with W1, and there is no ReLU, let's say, then this is just a linear transformation, right? So this is just Hx equals x plus W1x, and still it's a linear thing, and it won't make a difference without the ReLU. It won't increase the capacity of your model. So there has to be some ReLU for this to work. And if you add this ReLU here, let's do that. So x W1 ReLU Hx. Now this will implement x plus ReLU W1x. So in theory, yes, this will implement the skip connection or the identity transform if you initialize this with zeros. But since ReLU is always positive or zero, this creates a bias. That's why this is not preferred. That's why this is the solution. Here, you get this W2 outside of ReLU, which can give you zero or positive or negative values. But in this formulation, you won't get any negative values, so it's biased. That's why we need this design. There are two weight layers and a ReLU in between. It looks like maybe unnecessary to you, but this is the minimal necessary setup for the residual connection to work properly. This one? So there is no non-linearity here. So it's x plus W1x, and it is just a linear layer. Even if you insert a layer, it doesn't increase the capacity of your model. Remember the XOR problem. Linear models cannot solve it. And by doing so, they show that in Cypher 10, for example, this is plain nets, and as you stack up more layers, the error goes up. But with ResNets, it's the other way around. As you add more layers, your test error goes down. And the train error also, but it is very, you cannot see here. So, and with this technique, they were able to go up to 110 layers. So this is now the revolution of depth. Okay. Lower training error and also lower test error. And after this ResNet's proposal, it got the first place in all 5 main tracks: classification, detection, localization, COCO detection, and segmentation. These are very highly respected benchmarks. And even after that, it has had a huge impact, almost 300,000 citations as of today. And they also inspired other architectures, such as ResNext. This one is a ResNet block, classical ResNet block. This is the ResNext block. So remember inception modules? So ResNext actually combine residual connections with multi-scale processing, because you have the same input processed by different filters, 1 by 1, 3 by 3. Actually, it's all 1 by 1 here. But anyway, it makes it wider with different filter sizes. This is called the ResNext. There is also DenseNet, which creates all the connections, okay? So this input layer is not only connected to the next layer, but also next layer, and the other layer, and even up to the layer before the output. Okay? And this is called DenseNet. So traditional CNNs with L layers have L connections, but DenseNets have L times L plus 1 connections, because each layer is connected to all other layers. They have advantages. They alleviate the vanishing gradient problem. They strengthen feature propagation, encourage feature reuse, and substantially reduce the number of parameters. And they have shown very good results. So this red curve is ResNet, blue curve is DenseNet. So with the same number of parameters, let's say, it achieves much better validation error. And with less and less parameters, it achieves very good validation error. On CIFAR 10, it uses 3 times less parameters. But it's not being very widely used. So adoption of this network by the community is not very high, although it has all these nice properties. It must have some disadvantages that I cannot see here, but it's probably because of this L-square connections creates lots of complexity. Okay, let's take a 10-minute break and then let's look at the types of convolution. Okay, let's start. Types of convolution. You might ask, are there types of convolution? Yes, there are types of convolution. And here are commonly used ones. I'm sure there are more, but these are the commonly used types of convolution. For example, dilated, separable in terms of spatial and depth-wise, one-by-one convolution, also called the point-wise convolution, and transposed convolution, also known as deconvolution. Let's look at all of them one by one. Dilated convolution is something you use when you want to cover a larger area of the input image or the input tensor, but with the same number of parameters. So let's say you want to use a 3x3 kernel with 9 parameters. Actually not 9, 3x3 by, there should be some number of channels. But you want to cover a larger area. And if you want to do that, then dilated convolution is what you need to use. Here, the blue color indicates the input, green color is the output, and the dark blue locations here are the kernel. And as you can see, the kernel pixels are separated by 1 pixel. So they are 1 pixel apart. So they are dilated, okay? So it's still a 3x3 kernel, but it covers a 5x5 area. Okay, also called perforated convolution, dilated convolution, and there's a French name which I cannot read. There's also a French name. So this is dilated convolution. There is a parameter in PyTorch conv2d. If you give dilated equals to 1, you would get such a kernel. Okay. Separable convolution has 2 types, spatially separable convolution and depth-wise separable convolution. Let's look at the first one first. Spatially separable convolution is possible when you have a rank deficient matrix. For example, if you have this matrix as your kernel, as you can see, the columns, the second column is twice the first column, and the third column is the 3 times the first column. So the columns are not linearly independent. So this is a 3 by 3 matrix, but its rank is 1 because number of linearly independent columns is just 1. In that case, you can write this such a matrix using an outer product with a vector times transpose vector. And when you do that, you can achieve the same convolution effect by using this. You can achieve the same convolution by convolving with these two separate vectors. And it's shown here. So image is convolved with this filter, you get some output. But if you decompose this into this outer product and you first convolve it with this vector, and then you convolve the intermediate output with the raw vector, you would get the same output image. So you can think of this as a way of reducing the number of learnable parameters, right? Instead of learning 9 parameters here, you can learn 6 parameters. So this is called spatially separable convolution. Not being used very widely, okay? But this is just something you can be aware of, and this is possible, but not widely used. We talk about separable convolution because the depth-wise separable is being widely used, okay? So this one is the important one. So let's discuss what depth-wise separable is. In a normal convolution, if I want to convolve a 12 by 12 by 3 image using a 5 by 5 by 3 kernel, this 3 is important here because it should match the number of channels in the input, right? This kernel sees a 5 by 5 area, but also it sees the depth channels as well. And then you get an 8 by 8 by 1 output out of this using valid convolution. In depth-wise separable convolution, each channel is processed by a different kernel, okay? So we no longer have this kind of filter, but we have filters, one channel filters per channel, and then they give this corresponding output. But so far it's not interesting because it's the same number of operations, it's very similar. Let's introduce 1 by 1 point-wise convolution, and then we will combine depth-wise and one by 1, and that will make a difference. So 1 by 1 convolution is also called point-wise convolution. It only processes just one multidimensional pixel. And then this is usually used to change the depth of the channels, not the spatial dimensions, because 8 by 8 goes in, 8 by 8 goes out, but you can change the channels here, number of channels. And the number of channels here is determined by the number of 1 by 1 kernels that you use. Now let's combine depth-wise and 1 by 1. So it's in the bottom part, but let's look at the upper parts first. We have a 12 by 12 by 3 image, and we are convolving this with 5 by 5 by 3 kernels and 256 of them. I forgot to write it here. Okay. And then this gives us 8 by 8 by 256 output. This is the plain convolution that we know. But you can achieve the same effect. I mean, you get the same output by depth-wise convolution first, and then 1 by 1 convolution next. So depth-wise convolution, and then 1 by 1, 256 1 by 1 filters, you would get the same output shape. And why do we do this? Any ideas?
Reducing number of parameters.
Reducing the number of parameters. Can you see why is it reduced? Let's just compute only one pixel in the output. For that, we need to multiply 5 by 5 by 3 numbers, right? To compute just one pixel at one dimension. If you want to do the whole thing, then you also need 256 times. So this is the number of operations that you need to do for the upper part. For the lower part, to compute this, you again need 5 by 5 by 3 operations. And then after that, plus, so we need to add, to compute this, we need the channel 3 times 256. Now compare this with that. It's drastically reduced. So this is commonly used when you want to reduce the number of parameters in your convolutional layers. Okay, depth-wise separable convolution followed by one point-wise convolution. Okay. Last type of convolution is the transpose convolution or deconvolution, and it is nicely illustrated by this figure. We have again an input here, it's 2 by 2 input, and the kernel again 2 by 2. What do we do in convolution? We overlay the kernel on top of the input, take a dot product, and write it to the output, right? This is what convolution is. In deconvolution, a similar but different operation is carried out. First, you take one pixel in your input and multiply it with your kernel. And because this is 0, you will get 0, 0, 0, 0. And you put it here because it's the first location. In the second location, this 1 gets multiplied with the kernel and it is written at its location. Next, 2 is multiplied with the kernel and the values are put in that corresponding location. And finally, 3 multiplied by the kernel, put here in its corresponding location. And if you sum all of these things, this is the output. So this is called deconvolution. It's like a reverse operation of the convolution. This is used when, here's the question, what happens when the kernel, this one, is larger than the input? If let's say, I have a 2 by 2 input, but a 5 by 5 kernel, what would happen? Because of this operation, the output will also be large. Okay, so the larger your kernel, the output will be larger as well. And this idea is used in image segmentation. For example, this one is from ICCV 2015. Input image goes in here on the left, and through convolutional layers and max pooling layers, you reduce the image or summarize the image into a 1 by 1 and I don't know how many channels, but 1 by d depth. It's like a tube. Then from there, you can use deconvolution layers to upscale this 1 by 1 thing to the full size of the input image, as in here. Okay, so this is one application of deconvolution. You can use it in image segmentation. And since these deconvolutional layers has learnable parameters, which are these numbers within your kernel are learnable parameters. You can achieve image segmentation. I think this concludes the types of convolution. Do we have any questions so far? Okay. I encourage you to look at the Colab notebook on implementing a bare bones object detector. This is on the course web page. This one. So this shows you an example, something different than image classification, right? So far we have seen all of our examples through image classification, but this one is showing you an object detection example. Let me show you a example image here. So here we are trying to detect objects in three classes. We have a date class, fig class, and hazelnut class. There are three classes, and we have such images in this data set. You can consider this a toy data set. And for such an image, the corresponding label would be something like this. So in image classification, the label of each image was just a one-hot vector. Right? If you have C classes, it's a C-dimensional vector. Only one of them is 1, all others are 0. But in object detection, this is a more complicated task. The label looks like this. The label is like, again, 2D matrix, a spatial label. And at each location, for example, for the dates, it is represented with this light blue color. And at the location of dates, you have this light blue color. At the location of figs, you have this green color. At the location of hazelnuts, you have the yellow color. And if you can design a network which takes this input image and outputs this kind of colors at the correct locations, then you achieve object detection. Okay. So object detection involves both search, because you don't know where the object is within the image, and also recognition. So search plus recognition. Just a very simple application. So please go over this, and if there are things that you don't understand, we can discuss, but it's fairly straightforward. And this is the output of an object detection from the test set. So this is an image that the model did not see before. And these are the bounding boxes along with the recognized object classes. So this is the result of the object detection. Not 100% successful, but it's a reasonable performance. And also I provide some points, directions to improve, because you have lots of directions to improve the object detector. If you are curious, you can check these directions, and maybe you want to implement some of them. Okay. So we are starting recurrent neural networks. So we have completed a major topic, which is convolutional neural networks, and another major topic is recurrent neural networks. And if you looked at the syllabus, we are going to release homework 1 this week, tomorrow probably. But I will give you enough time, don't worry, to do it. And that homework will cover MLPs, CNNs, and a question with recurrent neural networks. So far we have seen MLPs and CNNs, and we said that CNNs are typically used for grid data, and RNNs are typically used for processing sequential data. Now you have a sequence, but this is not a rule set in stone. You can use both types of models to process either grid or sequential data. Okay, you can use a CNN to process sequential data, or you can use an RNN to process an image, for example. So depends on how you set up your problem, design your network. But these are typical things. RNN, if you have a sequential data, you go for an RNN. Well, not today. You go for a transformer today, but RNNs are important. I'm not sure if anybody is using RNNs today, LSTMs. But still, we have to learn LSTMs, RNNs. So the major difference from MLPs and CNNs is that MLPs and CNNs are feed-forward networks, which means we have an input X. It goes through a computational block, and then it goes through another computational block, and then another one, and this goes on like that. And now, at the end, you have an output. This is called feed-forward processing. There is no going back. It only goes in one direction. Okay, this is feed-forward. RNNs, on the other hand, you have an input, you have a computational block, another computational block, and maybe the output of this is fed back to as input to this, and so on. And this is feedback connections. So this is the fundamental difference. RNNs have cycles or feedback connections, but MLPs and CNNs don't have them. They are feed-forward networks. So if you remember parameter sharing in CNNs, which is the fundamental property of CNNs, which means if I have this input image and if I have this, let's say, 4x4 kernel, I use the same kernel weights for all locations in the image, and that's called parameter sharing. Okay, all locations share the same parameters for a given convolutional kernel. And of course, if you have another convolutional kernel, it has different parameters, but those parameters are also shared among locations. Parameter sharing for all locations. A similar idea is, RNNs have a similar idea, but this is parameter sharing through time. Okay. Let's say you have a sequence. This is your input. It consists of T elements. You can think of this as time. And you process each element of the sequence using the same parameters of your network, let's say. So you have a function f, which takes x, and it has these parameters theta, and those same parameters are used at every step. But there is also something called the hidden state, which I will talk about. And that carries out the summary of the sequence up to that point. Okay, so hidden states. Okay, so that hidden state is also something new, which did not exist with MLPs and CNNs. Okay, here is the mathematical expression for an RNN. Again, we represent the model or the neural network using the symbol F. And X is the input, H is called the hidden state, and theta are, again, the parameters, and these are the parameters that are shared through time. So let's understand this equation a little bit further. Function f is applied to the element of input at time t, xt. And it also takes h t minus 1. So hidden state coming from the previous time step. And then it outputs the new value of the hidden state, ht. This is a basic RNN. If you expand this function for a few steps, for example, let's say to compute H3, you would get such a nested function call. At the beginning, we have this f with hidden state 0, the first input, and then the output of this is processed by the second call of the same function with the input at time t, and then the output of this again is processed by the same function f with x3, and each call f uses the same parameters. And as a summary, what happens in practice is that you have this sequence from x1 to xt. That whole sequence is mapped to ht, the hidden state at time t. We can express this mathematical notation using graph notation. So you have x here, h here, and this thing with the black square means we are using the one time step previous of it fed to itself, and the unfolded notation is as such. So this black square is represent one time step. Because in the unfolded notation, the vertical elements are in the same time. So this is t minus 1, this is t plus 1, and the horizontal flow is through time. Okay. We said that this expression can be extended, and for each length of the sequence, this is actually implementing a function g of t, but this sequence of t length, an arbitrary length actually, because you can call this f many times as you want, is mapped to just a single thing, which is ht. So the whole input from x1 to xt is of arbitrary length, but ht is fixed length. So ht is a lossy summary of the task relevant aspects of x1 to xt. So it's actually summarizing the task relevant aspects, whatever your task is, into ht, and that's called the hidden state. And this is a lossy summary because t can be anything. Your sequence could be a novel, a whole novel, a Tolstoy novel, and each word, you can consider each word as X, and an LSTM or an RNN can read the whole novel and output just one HT. That's the lossy summary of the whole book. Because of this flexible processing scheme of RNNs, you can solve a variety of problems. For example, you can solve a one-to-one problem, and this is a basic machine learning. You get a fixed size input vector in and a fixed size prediction vector out, for example, image classification. You can solve image classification using an RNN, theoretically. You can have a sequence output, so a fixed input and a sequence output. For example, this could be image captioning. You give it an image, and then the RNN outputs a descriptive sentence describing the contents of the image. And the content could be a paragraph, could be a few sentences, just a sentence, so it's of arbitrary length. Many to one, you can have a sequence input, for example, a sentence in or a paragraph in, and the label out, sentiment label. This is done using Twitter analysis, for example. If a tweet is a positive or a negative thing, happy or sad, I don't know. But an arbitrary length of words in, just one thing out, a label is out, many to one. You can implement an RNN to do that. Many to many is also possible. And this is always done in machine translation. There's a sequence input, could be a sentence, a paragraph in one language, and the sequence output is in another language. And the number of words, sentences do not need to be the same. So an RNN is very flexible. Many to many video frame classification and so on. So this is an RNN in theory can do actually what a computer can do. It's that general. So a recurrent network that maps input X to output sequence O using a loss function L is here, and the label sequence Y. You can try to draw the equivalent unfolded network as an exercise. I will just show it to you here. It's a very easy thing to do. But this is the most general form that an RNN can take. It has a sequence of inputs. It has a sequence of outputs. And for that output, there's a sequence of labels that are provided by some data set. And you can compute a loss value at each time step. This is the most general setup that you can have. This RNN is universal. Remember the universal approximation theorem, Seibenko's theorem, MLPs are universal approximators, universal function approximators. And RNNs are actually universal in the sense that any function computable by a Turing machine can be computed by such a recurrent network of a finite size. So these are even more powerful. With MLPs, we just approximated functions. With RNNs, you can compute any function that a Turing machine can. So this is as powerful as a computer, actually. In theory, of course. But this is a very nice property to have. So let's look at the update equations. What it is actually doing. There are several update equations going on here because, okay, let's look at input to hidden transition. So let's look at this arrow first. So from the input, we compute the hidden state, right? And the way to do that is, as you can see, there are two parameters you can see here. The first one is U from between X to H, and the second one is W from HT minus 1 to HT, because remember, this was a time step, right? And these two matrices are used in this update equation. So W times HT minus 1 plus U times XT. So this is the input at time T. This is the hidden state at time T, I mean, coming from the previous time, plus a bias term. And this is called AT. If you pass AT through a nonlinearity, tanh, for example, sigmoid or ReLU, you get the hidden state value. And this is how you update H using two parameters, U and W. Similarly, you can compute the output by a bias term C plus V times HT. This is another parameter, V. And your loss function could be, or your output prediction, Y hat, is the softmax of OT. Here, the tanh and softmax are just example choices, but the total parameters of this network is the concatenation of U, V, and W, because that's all the parameters that this RNN has. you can write a total loss between the sequence of input and the sequence of output. So, and this tau, there's no fixed size for it. It could be just one word or a sentence or a paragraph. And here, negative log likelihood loss is just an example. You can have any loss you want. So at the end, what it is doing is this function f is taking input at time t, hidden state at the previous time, processes them with these parameters. And remember, the parameters are u, v, w. And this output, what does it output? It outputs actually the hidden state, and also it also has an output O. Okay, and this and that. And then depending on your task, you can design a loss function and write that loss function as a sum over your data set or as an average. And then what do? The usual thing, backpropagation and gradient descent, right? So usual thing. To do that, we need the gradient of L with respect to model parameters. So we need the gradient of L with respect to theta. And as you can imagine, this is computed using backpropagation, but it's a little bit more complicated because now we have time dimension, and it's called backpropagation through time. The derivation is a little bit involved. I'm not going to go through it here. To show that it's how it is involved here, let me show you why is it difficult. So let's say we want to compute the derivative, the gradient of loss with respect to u, let's say, which is a parameter in the model. And u is used between x and h, right? And L is here. So the difficulty comes from L3 depending on u through several branches. For example, L3 is affected by this calculation here, as well as this calculation here and that calculation here. And similarly, if you want to calculate the gradient with respect to W, let's say gradient of L3 with respect to W, it is affected by this calculation here and that calculation here. So you have to take the backpropagation through time, and what you end up with is this kind of result. So the derivative of loss with respect to the hidden state 1, let's say, it is derivative of loss with respect to O1, derivative of O1 with respect to H1, and these are fairly straightforward. No problem, because within the same time step, taking the derivative is just straightforward, easy, nothing different. But the other term has a recurrence relation here. So derivative of L with respect to H1 involves a term of which says the derivative of L with respect to H2. Okay, and this is called backpropagation through time. But you can write the expression for this using this pattern again, and then it just works out. The only thing is that it's much more complicated than the backpropagation in MLPs and CNNs, okay, because of the time dimension. Each parameter is shared through time, It is used at each time step, and because of that, it brings this complexity. But fortunately, these are all implemented in the libraries, so you don't have to. But we should know how this is derived. Okay, I don't like skipping it like this, but it will take too much time doing this here. Okay, let's say we did the backpropagation through time, and now the question is how much time and memory would it take to compute the gradient of L? Any ideas? I'm actually asking the time complexity of backpropagation through time. Let's say for a sequence of capital T. If you have a sequence of capital T, how much time would it take to compute the gradient of L? T square. Why do you think it's T square?
T, the previous topic also, T minus one.
Mm-hmm. Yes. Okay. A naive implementation can take T square, but if you properly cache, yes, if you cache the intermediate steps and reuse them, it actually is on the order of OT. For a sequence of size T, it takes OT time and OT memory, so it's actually pretty efficient. So no problem in terms of efficiency, but the problem is the computation cannot be parallelized because the last output in your sequence, output element, depends on everything before it. And you cannot parallelize this computation. That's the bottleneck with RNNs. So they, because of this bottleneck, and this bottleneck is happening because of the recurrence between hidden states here. So this arrow is actually causing the blocker for before the parallelization. And this is actually the reason RNN is very powerful, Turing complete, but it's also very expensive to evaluate and learn because of the not being parallelized. It's not because of the time complexity of backpropagation through time, but the parallelization issue. Can we avoid backpropagation through time? The answer is yes. If you change the architecture from, remember, the original architecture was like this. There was a feedback loop to the hidden state, right? It was like this, but that causes the problem for the parallelization. If you instead take the recurrence relation from the output to the hidden state, like this, now this you can parallelize the training of this using a method called teacher forcing. We will talk about it now. But let's talk about this specific architecture first. In this RNN, which has a recurrence connection from output to hidden state, O is the only information that captures all the information about the past. Previously it was H, now it's O. And since O is the network output, it is typically has a specific format. For example, it could be a vector or a label. So this RNN is less powerful compared to the previous architecture, which has the recurrence relation between the hidden states. The current state indirectly affects the next state through O. And this architecture cannot simulate a universal Turing machine. So it's less powerful, but easier to train because this can be parallelizable, as we will see. less powerful but more efficient training, because for these type of networks, there is a training technique called teacher forcing. And here it is. In teacher forcing, during training, so this is train time. So the figure on the left is train time, this is test time. During train time, each time block, let's say, is getting an input from the label of the previous step, not the hidden state or the output. And because of that, since the labels are already provided in the data sets that you train on, you can now train each of these time vertical, these blocks in parallel, because the current label and the previous label, you can assume that it's already provided in the data set. This is called teacher forcing. It is less powerful than the standard RNN, but training can be parallelized. During test time, since you don't have labels Y, you get the connection from the output of the previous step, like this. So maybe abstract for you, but think of X as the words in a sentence, okay? And think of Y, the labels, as the, what? I don't know. What could be the, word tags, but what are the word tags?
Some magnetic recognition.
Yes. Named entity recognition, yes. Each word has a tag. Yes. And why are the tags? So these are all available to you in the data set beforehand. That's why you can parallelize this training. For each word, you know its label, and you know the label of the previous word. Now you can train this network in parallel. But if you did the standard thing, which took this connection, then you have to consume the whole sentence in order to, compute the output for the last word. Okay? And that's the bottleneck. Okay. We have considered causal RNNs, which means output at time t depends on the past input, but you can have bidirectional RNNs. State at time t captures information from the past. This is causal. What if you want the output to depend on the whole input sequence? You can achieve this by using bidirectional RNNs, which is shown here. This path, the H, as you can see, has the from left to right flow, and there is another set of hidden states which has the reverse flow from right to left. Okay, and this now the output here, the output at time t depends on the future elements through this connection, and also past elements through this connection. So this is called bidirectional. You can make it bidirectional. Yes. Okay. Any questions so far? RNNs always sound a little bit abstract, but yeah, if you do some implementation, then it's grounded concretely. Now let's take a 10-minute break and then continue in the next hour. Okay, let's continue with RNNs. As usual with any neural network, you can make them deeper by adding more layers, right? And here, there are three locations where you can make RNNs deeper. There are hidden to hidden connections, there are hidden to output connections, and input to hidden connections. And in each of them, you can add more layers or skip connections, as in residual networks, to make them deeper. For example, you can add depth to hidden states. You can have two hidden state vectors instead of just one. You can make each processing block an MLP. Instead of just one arrow with black square, you can have one more node here. This increases capacity, but optimization might be more difficult. To mitigate the difficulties, as we discussed in the residual connections, you can add skip connections such as this one. Okay. So some straightforward, obvious ways of adding depth to your RNNs to increase their capacity. Now let's talk about the long-term dependencies challenge, which is a very central and fundamental question, which RNNs try to solve. And to solve this problem, LSTM, long short-term memory networks, were proposed. LSTM is a type of RNN, the most famous type of RNN. But there are other RNN variants too. And the invention of transformers, self-attention and transformers, are because of this problem. So they solve this problem in a much better way than LSTM does. Okay, so that's why it's important to understand what this problem is. So if we have more depth or longer sequence, then we have more vanishing or exploding gradient problem. I will show you mathematically why this is the case. But let's first understand the problem. So let's say we are developing a language model that predicts the next word based on the previous words. A short-term dependency is when you have a sentence that is short and let's say the sky is blue. So when you want your model to predict what word should come here, because it just saw the sky, it can predict that it should put blue there. And for example, here, it can easily predict that the word here should be white because it's talking about the clouds. This is short-term dependency. The answer, blue or white, depends on just a few words back. It's a short distance. But it's not always that easy. Let me give you a long-term dependency example. France is my home country. I speak fluent French. In this two-sentence input, if I wanted to predict this word based on the previous words, now this is a long-term dependency. Because the answer is probably will depend on the word France, but it is now far away from the output, right? The distance between the influencing word and the answer now has a big distance. And of course, you can make this even more challenging. There could be a few sentences in between the influencing word and the answer. This is called long-term dependency. You should somehow pass this information in France up to this word, because in order for this word to be correctly predicted, okay? So This could be the France word here, x0, and the output here should, the expected output should be French. Well, this is the hidden state, but you can think of O as well. So the dependency is through several time steps, and this is called the long-term dependency problem. And as the distance gets larger and larger, because of the vanishing gradients, exploding gradients, this problem becomes difficult to solve. We will see how LSTM and GRUs solve this problem. Actually, the challenge of long-term dependencies is not specific to RNNs. It can happen for MLPs and CNNs too. But the problem is more serious for RNNs because first, let's look at the feed-forward network, which is MLP-CNN. In a feed-forward network with T layers, each layer has different and independently initialized weights. Remember, He initialization, Javier initialization. Variance can be controlled. Theoretically, vanishing exploding gradient problem can be avoided by controlling the variance of the initialization. But in a recurrent network with T layers, we will have WT, which will either vanish or explode depending on the initial magnitude of W. I will show you mathematically. Theoretically, RNNs should be able to learn long-term dependencies, but it would either take a lot of time because the gradient signal from France to French gets very small or vanishes, or it will just fail due to numerical problems, going to 0 or very high numbers, not a number eventually, NANs. Okay, why is this happening? So consider the relation between the previous hidden state and the current hidden state. We get the current hidden state from the previous one by just a matrix multiplication. Of course, there's a nonlinearity as well. But for ease of illustration, we are just dropping it here. So the relation between HT and HT minus 1 is this matrix multiplication. The relation between HT and H0, the initial hidden state, is because of this recurrence relation, it's repeated matrix multiplication. It's like the matrix W to the power of T, because we are considering T time steps. If we do an eigenvalue decomposition for W, Q lambda Q transpose, and take the T power of T here, you get this. And notice that the lambda matrix, which is the diagonal matrix of eigenvalues, right? You take the power of these scalar values here, power of T. And what this does is, if you have small values, if you keep multiplying those small values, they will just vanish, go to 0. If you have, so if you have all 1 values that are close to 1, that's fine, because 1 multiplied by 1, it will be stable. But if you have values close to 0, they will tend towards 0. If you have values larger than 1, they could easily become huge numbers, exponentially growing. This is the source of vanishing or exploding gradients problem, repeated matrix multiplication. So this happens in MLPs, CNNs, but RNNs especially, because we are now talking about a sequence, and through the sequence we are multiplying the same matrix because it's shared through time. So we have 2 problems, exploding gradients and vanishing gradients. Exploding gradients is usually solved by gradient clipping. This is a solution that works in practice. So gradient, if the magnitude of the gradient is larger than a threshold, this is an hyperparameter, then what you do is you make it unit magnitude or just change its magnitude, but the direction is the same, you reduce its magnitude. This is called gradient clipping. An example is given in this paper. If you take small steps, you can get to a good local minima. But if you take a large step when you're here, this could take you take you to a very high loss location, which undoes your progress made so far. So gradient clipping works for exploding gradients. What about vanishing gradients? There are, of course, several solutions proposed. One of them is regularizing the gradient. I will just skip this because this is not being used widely. The real solution, the vanishing gradients, is the LSTM networks, long short-term memory networks, or other gated RNNs such as GRU. Now we will go through them. And the trick that solves this problem is the idea in ResNets. The skip connection, you remember? Because of the skip connection, the input just passes to the output with an identity transform. It could do that. And that capability actually solves or drastically reduces this vanishing gradients problem. So we can say that LSTMs, GRUs are RNN equivalents of ResNets. Okay, so the same idea applied through RNNs. So in a standard RNN, a repeating module is here. What you do is the computation carried out is HT, hidden state, is some nonlinearity, let's use sigmoid, some parameter times current input with previous hidden state. Something like this. This is what a standard RNN does. I will first talk about the GRU because it's much cleaner than LSTM, and it's a more modern version, 2014. LSTM, I think, has some redundancies. Let's introduce GRU first. So remember this is the standard RNN computation. Hidden state is calculated by nonlinearity, a matrix multiplication of current input and the previous hidden state. And compare that to the update equation of the GRU. Look at that. Here in this equation, we have a gate. This is called a gate. And this gate is, look at how it's used. So there are two terms, HT-1 and H tilde. They are combined with ZT and 1 minus ZT. So depending on the value of ZT, either one of them gets dominant or not. Okay. And it is possible to get, for example, if you set ZT to 0, it is possible to get HT equals HT-1. So this is the idea in residual connections. So the previous hidden state can just pass without being changed to the next state. So identity transform. And this is controlled by this gate ZT, and ZT is itself a function of, again, the current input and the previous hidden state parameterized by some matrix WZ. An intermediate variable RT is again a function of the current input, and HT-1 has its own parameter WR. And H tilde here is again a function of previous hidden state R and the current input XT. So you get the idea here, right? The RNN block itself computes the value of ZT first, and that value decides on how much of the previous state to pass and how much of it to just forget. So that is the idea. And
So I don't understand what RT.
RT is a intermediate variable that they compute, and it is used here.
It's still a calculation.
Mhm.
Why do you multiply RT in previously?
I think this is a design. You can design a GRU where H tilde is just tan H, another matrix H with HT minus 1 XT. This is also possible. RT is just adding more parameters. Yeah. So this is also possible. The main idea here, let's say, is also possible. The main idea here is the gated, idea of gate. So gate, this Z is a gate and this Z is a gate. How much of the newly calculated state H tilde and how much of the previous state to combine is decided by the gate. And this gate is able to pass the previous state intact, as in residual networks. So when you do this, it mitigates the vanishing gradients problem because it can pass the previous hidden state to the next stage without changing this. Okay, it doesn't have to make repeated multiplications. Okay, so this is GRU and LSTM, which is an earlier proposal, 1997, is very similar to GRU. Actually, GRU was inspired by LSTM. It's a simplified version of LSTM. LSTM, as you can see, is complicated. This is the machinery inside LSTM. Let's try to look at what's happening inside. The key idea behind LSTM is cells can implement the identity transform. This is the key idea in ResNets 2. So they define something called cell state C. So we already have hidden state H. Why do you define another cell state C? I don't know. But there is cell state and hidden state as well. So both of them exist in LSTM. And because of the gating mechanism, CT equals CT minus 1 is possible. And this is called the identity transform. So if you set the gate, if the RNN or LSTM decides to set the gate in certain values, then passing CT minus 1 intact to CT is possible. And this capability is the key to address vanishing gradients problem. So okay. There is a forget gate, FT, and there is an input gate, IT. Forget gate is a function of the current input and the previous hidden state. And similarly, input gate also is a function of the current input and the previous hidden state. They have their own parameters, of course, learnable parameters. These are also parameters, bias. And together, these two decide how much of the previous cell state and how much of the newly computed cell state, CT tilde, should be used, in what proportions to combine these two in order to get the current cell state. Okay? And C tilde is a function of, again, the current input, which is xt, and the previous hidden state, ht minus 1. So gating mechanism, again, as in GRU, but this is, as I said, more complicated, and it's not necessarily better than GRU. There is another gate, which is called the output gate, and this decides how much of the computed cell state should be given to the current hidden state. And overall, this is the equations that govern LSTM. You have a forget gate, you have an input gate, you have an output gate, and the current cell state is calculated by this update equation. It uses the previous cell state and the newly computed cell state and combines them using the forget gate and input gates, and the output is decided by the output gate here. So this is LSTM. Let's look at GRU again. Now, I talked about this, but now, since you know LSTM, now you can compare GRU and LSTM. This is much more simplified because it combines the forget and input gates into a single update gate. In LSTMs, look at that. There's a forget gate, there's an input gate, and these two are not related to each other by, one of them is not the one minus the other. But in GRU, this is simplified. Look at the ZT here, 1 minus ZT and ZT. And it merges the cell state and hidden state. So there's no CT because it's not really necessary. There's already an HT. So cell state is not necessary. Yeah, the resulting model GRU is simpler than LSTM, and in practice, GRU works as good as LSTM. So if you have a project that you need to use an LSTM, for example, time series processing, you can go for a GRU instead of LSTM. It has less hyperparameters to tune. It's simpler. Okay, any questions about LSTMs? Yes. How does it? It solves the vanishing gradients problem because it can implement because of that. It can take the previous hidden state and it can pass that without changing it to the next step. And this is, they say that this is why it solves vanishing gradient problem. It is similar to the, remember, the ResNet idea? Do you remember the ResNet idea? It's the same thing. The residual connection is here. So in ResNets, with the residual connection, you can increase the depth from, previously it was 16 to 19, and ResNets took it to 150. Same thing is happening here. You can now process more longer sequences without vanishing gradients. Yes. Yeah, so the question is there an advantage of using this instead of a transformer? I would say no. There's no advantage. But there could be, let's say, a very simple time series data, like just numbers, a number at a time or a few numbers at a time. Maybe in that case, this is a simpler model. It could give as good performance as a transformer. I don't know. But yeah, transformers solve the long-term dependencies much better than LSTMs.
I will talk about the RSTM, the RNNs, and LSTM as output parameters and the transformer parameters. Because transformers are the sector.
So the question is, do transformers have more parameters than LSTMs? It depends on your design. We cannot say that for sure because how many layers are you going to use? And what are the, in an LSTM, you can make this also a very large number of parameters. You can add depth here. Okay, so if there are no questions, I can give the quiz. So there are two problems here. You can choose to solve one of them.